I'm Tan.
Hi, I'm Shuhada.
Today we are going to talk about complementary metal oxide semiconductor or CMOS.
Let's start with the CMOS structure. CMOS combines both NMOS and PMOS on the same substrate like this. This is an example of CMOS with P substrate and envelope. The left part here is the PMOS and the right part is the NMOS. Just like the normal NMOS and PMOS, both of them have a gate terminal, source terminal, and drain terminal. The thin outside layer here acts as dielectric material. The only difference is that both PMOS and NMOS are now on the same substrate. We can see that the PMOS is built on envelope on the P substrate.
Interesting. Shada, what is this B terminal here?
Oh, the B terminal is the body terminal which is used to adjust the threshold voltage of the CMOS. The voltage difference between the source voltage Vs and the body voltage Vb can affect the threshold voltage Vb. So we can think of the body terminal as the second gate that helps to determine how a transistor turns on and off. We will dive deeper in this later.
So, now let's hop on to the operation of CMOS. But before that, let's revisit how NMOS and PMOS works. This is an NMOS with the body and source grounded and the drain terminal connected to a VDD of 5 volt. When there is no bias applied to the gate, there is no potential difference between the gate and the substrate or the body. So nothing happens and the NMOS remains off. However, if we supply a gate voltage of 5 volt to the NMOS with the same configuration, we see that now there's a potential difference between the gate and the substrate. This will accumulate the positive charges at the gate, which is the red color part, and attracts the negative charge from the P substrate near to the gate, forming a channel that allows current flow. And now the NMOS is on. PMOS works just the other way around. Let's look at this PMOS with the body and source terminal connected to the VDD of 5 volt and the drain terminal grounded. So when there's no bias applied at the gate terminal, there is a potential difference between the gate and the body. Therefore, negative charge accumulates at the gate terminal here and attracts the positive charges near to the gate, forming a channel that allows current flow. So the PMOS is on when there is no gate voltage applied, just opposite to the NMOS. If we apply a gate voltage of 5 volt, the gate and body are now in similar voltage level, or simply there is no potential difference between them, and therefore nothing happens and the PMOS is off. In summary, when there is no bias at the gate, NMOS will be off but PMOS will be on. If there is bias at the gate, NMOS will be on but PMOS will be off. Hope that's recall your memory on NMOS and PMOS. And now comes the interesting part. What if those circuits we see just now are applied to CMOS just like this? So we see that there is no gate voltage applied, but the NMOS is on, PMOS is off. The PMOS is on, but the NMOS is off. When there is a gate voltage applied, the PMOS is off and the NMOS is on. One on and the other goes off. This is one of the important characteristics of CMOS.
Great! Let's move to the advantages of CMOS. CMOS has the least amount of power dissipation as there is no continuous current path from the positive terminal to the negative terminal through the circuit. CMOS reduces the circuit complexity as it requires fewer components. CMOS also produces less heat compared to the other transistors. In ideal state, CMOS dissipates almost zero or no power. This means that it only dissipates power while switching. Less dissipation results in low power consumption. CMOS is stable in a wider temperature range, which is around negative 55 degrees to 125 degrees Celsius compared to the other logic circuits. CMOS has the highest noise immunity, which means it can still function well in the presence of noise interference. Lastly, CMOS has high fan-out feature that measures the load ability to a logic gate. Fan-out specifies the input gates driven by the output of the other gate.
As the advantages it offers, CMOS were widely implemented and have replaced NMOS and bipolar processors for nearly all digital logic applications. CMOS technology has been used in integrated circuits, chip designing, microprocessor designing, ASIC designing, and CPU designing. But Shraddha, do you know how CMOS is fabricated?
Yes, of course. Let's jump to the CMOS fabrication process flow using N-well technology. In N-well technology, an N-type well is diffused on a P-type substrate. Let's start with a blank wafer, typically a P-type substrate, and then the wafer is covered with a protective layer, silicon oxide, and then followed by a layer of photoresist material. So the wafer is then exposed to the UV light using N-well mask. This process is known as photolithography. Photoresist material changes its property when exposed to light. Then the area exposed to UV light is removed using organic solvents. This etching process is repeated to remove the uncovered oxide using hydrofluoric acid. Then the remaining photoresist material is removed using a mixture of acids. It is necessary so that the resist doesn't melt in the next step. So the N-well is formed within the P substrate using the diffusion or ion implantation. Again, the remaining oxide is removed using hydrofluoric acid. Now the wafer is back to bare wafer with N-well.
So now let's fabricate the gates. The process continues with chemical vapor deposition or CVD of a very thin layer of gate oxide here, typically less than 20 angstrom, and a polysilicon layer here. Again, we use photolithography to pattern the polysilicon to here, to this. So the next step is to dope the N+ region. We use the gate oxide or polysilicon to make the region for doping, just like this, to this, again using photolithography. Polysilicon is more favorable than metal for self-aligned gates because it doesn't melt during the later processes. So the N+ region is formed through the N diffusion or ion implantation process. And now let's strip off the oxide to complete the patterning step, just like this. The next step is to fabricate the P+ region, and the P+ region is formed using similar step as the N+ regions, which is masking using photolithography, then P diffusion and ion implantation. And now we are left with the contacts. So the chip is covered with thick film oxide like this, and the parts where the contact is needed are etched off just like this. The last step is to perform metallization to form the contact, and now our CMOS is completely fabricated.
Other than N-well CMOS, we have P-well CMOS, which is just the opposite of N-well CMOS and the twin-type CMOS, which have both N-well and P-well on it to preserve the performance of N-type transistor without degrading the P-type transistor. It can also handle latch-up efficiently.
So that's all for our video today. Oh, by the way, have you seen a CMOS before? If no, do check out our 3D CMOS AR, and you can now have a CMOS in your tablet. The link to the AR is at the description box below. Do check it out. And thanks for watching. Bye.